Now that we know the notion of subgames and subgame perfect Nash equilibrium, it is very important to talk about what is the computational cost. So we have discussed this for PSNEs and MSNEs, and we have seen that the MSNEs are hard to compute. And then we discussed about correlated equilibrium, where it is easy to compute. Now, what is the computational complexity of finding Spne? So it is the same example again, and here I have just repeated the backward induction algorithm. Just so now you can think about what is the number of computations or comparisons that you need to do. So essentially, you'll have to parse the whole tree at least once. So let us first try to understand what are the advantages of this Spne, the idea of subgame perfection, and then we can also discuss about what are the limitations. Now, one thing that we must already observe, that if you are given a finite perfect information extensive form game, where the depth of this tree is finite, then by using this backward induction algorithm, you will always find a subgame perfect Nash equilibrium. In other words, subgame perfect Nash equilibrium is guaranteed to exist in this kind of games. So of course you can write this down formally, but the idea is essentially based on the algorithm of backward induction itself. It has to return something, and it will return something which is non-empty. Therefore, the Spne will always exist for this kind of games. And this also gives you some answers. So we have seen that pure strategy Nash equilibrium might not exist in games in general, but there are some classes of games where PSNE is guaranteed to exist, and perfect information extensive form game is one such example where the pure strategy Nash equilibrium is guaranteed to exist, because all Spnes are also PSNEs, right? Now, the algorithm to find Spne, this backward induction, is also quite simple. It might be computationally complex, but it is very easy to explain. And that gives you sort of a kind of a downside of the computational cost. You see that to find the Spne, you'll have to parse the whole game tree at least once. Otherwise, you cannot find out an Spne. So that is really computationally expensive. So just to give you a kind of a context, the game of chess has roughly 10 to the power 150 vertices in its game tree, and it's needless to say that this number is larger than all the molecules in the on Earth. So therefore, even if you have a reasonably fast computer, you won't be able to find out the Spne of a chess game. So this brings us to the question that we have asked at the very beginning. So if we could actually solve this game using a super fast computer, then we could have found out what is the optimal strategy. We could have found out whether there exists. We know that one of the three statements for chess is true. We could have actually computationally found out what is that strategy, and then the game of chess would have been a very boring game, because you know what is going to happen in that game. Now, definitely for smaller games like the tic-tac-toe, you can actually write down all the strategies, all the vertices of the game tree, and also find out what is the PSNE, and that could be a good exercise. You can either do it by hand, but if it is pretty large, you can do it using a computer, and for that it will not be a very large amount of computation, because the game itself is very small. So that is one disadvantage. The concept is nice, but for certain games, particularly for real world games which are large enough, the computation complexity is clearly prohibitive. The other criticism that is often put forward in the context of the extensive form games or its solution concepts like Spne is about the cognitive limit of real players. So, for instance, here is a game which is very often used to give a counter example for the notion of Spne. This is called a centipede game. The name comes from the structure possibly. It looks like a centipede. But the whole idea is there are two players, player 1 and 2, and they are taking turns alternatively. Now, player 1, both of these players have two actions at every stage or every history of the game, which is go across or go down. And the game tree essentially tells you what are the utilities. Right? Now, the first thing should be to find out what is the Spne of this game. So now we can use backward induction and find out. So if you look at the last stage, player 1 is playing. It has two choices, A and D. It knows that in playing D, it gets more utility than playing A. So therefore, this is the better out of these two things. Similarly, you can see that if that is the case, player 2 should also play down. And you can go back and see that for every player, the best response should be to play down. So that is the prediction. Now this game has been experimented extensively in real world scenarios for various kind of populations. So it could be random participants, university students, chess grandmasters, and so on. So most of the people, so even though, so you can see that the prediction, what is the prediction of a Spne is so every player should play D. So therefore the game should not continue at all. It should end right away. So when the player 1 is given this choice, player 1 should play down and the game should end at that point. But quite interestingly, most of the subjects, whether they are random participants, university students, everybody except the grandmasters, they continue until a few rounds. It does not end at the first round. It is clear that people do not play subgame perfect Nash equilibrium, and there are various reasons which has been suggested as the reason for this thing. So all these things are kind of behavioral aspects. So people can be altruist, that they trust the other person more and then do not want to do the down and end the game at the very first round. The second thing is the limited computational capacity of individuals, which is like a cognitive limit. They might not be able to find out the Spne and therefore will not be playing the Spne. So the incentive difference is also, so it has also been experimented with larger differences in incentives. For instance, if you multiply all the utilities by 10 or 100, then the experiment, does it give a larger propensity of playing D? It has been seen that yes, when the utilities are much larger, it indeed plays, so people do play D more often than playing A. And it is also observed that typically people never go till the last round, so they do play this down strategy at some intermediate round. So they near the end of the game, they can actually find out what is going to happen and do some sort of a backward induction to play D, but they do not do it all the way till the beginning. So this is in principle somewhat related to the guess the 2/3 of the average game, where people do some sort of a iterative reasoning, but they do not go all the way until the end. So there is another criticism. So this is you can say that the empirical criticism for subgame perfect Nash equilibrium, that people do not play in the way Spne is guaranteeing. But there are some other criticisms also from the theoretical aspect. So look at the definition of Spne. It says that what action would a player play if a game reached at some history. So we are not worried about which history we are looking at. If the game ever reaches that history, it should the player should pick this action, which should be a Nash equilibrium in that subgame. But the equilibrium concept is essentially contradicting that fact. It is saying that you cannot really reach that history. So look at the example of AH that we AG that we have discussed, right? So player 1 was playing A, and then you are giving this the action G, but because player 1 is playing A, the game can never reach this subgame. So isn't it some sort of a flawed solution concept in itself? So that is another criticism. Just to give you a kind of a the ups and downs of this SPNE, there is no kind of very clear answer to any of these questions, and there are no better equilibrium concepts. So SPNE stands, but maybe it is not without its flaws. So in the next module, what we are going to discuss is we will extend this idea of subgame perfection, or the perfect information extensive form game, using the idea of player beliefs. So in this setting, we have assumed that everybody can observe everything, but maybe in certain kind of games, we have also given some examples previously. People do not observe the actions of all the players. Not all the histories are observable. So in that kind of settings, we introduce something called a player belief. They believe that the other player is, the game is in this state, so the other player might have played this action or something else. But that is anyway a noisy information. So how can we define the game concepts and its solution concepts, equilibrium concepts, when the players have beliefs?